So I said that the motion of an object depends on the forces just on that object. So let me draw a situation here. Let's say we have a filing cabinet. And let's say I'm trying to move that filing cabinet. So got my hands on that thing and I'm putting my weight into it. And again, Newton's third law says for every action there's an equal opposite reaction. So my push on the cabinet is equal to the cabinet's push back on me, which again feels like it's wrong. It feels like, then how does the cabinet ever move? If when I push harder, it pushes back harder, how does it ever move? Well, the motion of the cabinet depends just on the forces on the cabinet. So let's think, what other forces are acting here? Well, there's my push, there's the push of the cabinet on me and the push of me on the cabinet. There's some friction for sure. So the floor is acting on the cabinet this way. There's weight for both of us. There's friction on me. There's the carpet acting on me, right? There's the cabinet acting on the carpet. If I get this thing moving a little bit, there's going to be some drag. Probably not going to happen. My point is this. There are lots of forces happening here, right? If I'm pushing any up or down at all, there's some kind of friction, right? And that the other kind of, the other half of that friction, the action-reaction pair to that friction is acting on the cabinet. So if I want to know what's happening to just the cabinet, I need to identify just the forces on the cabinet. So one thing that we do is we isolate the cabinet, right? So let's draw a picture of just the cabinet. That's a terrible picture of a cabinet. Well, that's a point mass approximation for the cabinet, right? And actually, for now, that's pretty good. And there are forces acting on that cabinet, and they act in all sorts of directions, so I might want to draw some axes here. In fact, I could be like super careful about it, and I could draw some axes. So there's a y-axis, and there's an x-axis. And then I could draw all of the forces on this cabinet on that axis. What are the forces? Well, I could make a list of them here. We've got weight. There's going to be a normal force, right? Kind of acting that way. So there's normal. There's friction. And there's this push, which is technically a normal force from my hand. But let's just call it push for now. That's probably fine. So I could put all of these forces on this diagram, and that would help me see two things. One, it would help me visualize all the forces acting on just the cabinet, which helps me to identify how the cabinet is going to move, right? The forces on me do not affect the motion of the cabinet. Even though there are forces on me, the forces on me affect the motion of me. And the forces on the carpet affect the motion of the carpet. But the carpet's connected to the house, which is connected to the earth, which is connected to the knee bone or something. Okay, so I would put these forces on this diagram. Weight acts down, so there's weight. And normal acts like this way. There's normal. The push is here. Sometimes do F sub P, and then maybe some friction this way. And then this lets me identify the sum of the forces, which is going to lead to an acceleration. What we've drawn here, the vectors, the force vectors on this set of axes, is called a free body diagram. So those words together are a little cumbersome, but all it really means, a free body diagram, is a representation of an object by itself, right? So I'm only picking one object. Now, I could take two objects together and call it one object and draw a free body diagram for that. But whatever I'm doing, I'm isolating something and drawing all of the forces on it on some axes. And in fact, the lecture handout here has a nice description of the process for building a free body diagram. So choose a single object, identify all the forces on it, draw some axes. So I drew this guided by the horizontalness of the ground, right? But you could imagine, like, if you're on an incline, you might want to tilt the axes for the free body diagram. In fact, there's really only one specific example I can think of where I don't tilt the axes when there is an incline, but we'll get to that in a future chapter. So then we can draw all of the forces on these axes. The one last thing I want to mention is we kind of want to be careful about lengths of the vectors, and you'll see why in a minute. If you don't know the relative lengths of the vectors, you can just draw them. But sometimes it's nice to have these to scale. Helps you to know if your final answer is relatively correct. Okay, so let's do a couple examples. I feel like I did that one already. Okay. Here, example number 10. A chandelier hangs from two support chains from the ceiling. Each chain makes a 30-degree angle with the ceiling. Draw a free body diagram. So the first step of any physics problem is to draw a picture. So that's what I'm going to do, is draw a picture. So here's the ceiling. This is it's not a trick or a technique. This is a method I learned a long time ago just to show a fixed surface. So that's what I'm doing when I put those little hash marks up there. And the chandelier is connected by two ropes, right? Each making a 30-degree angle with the ceiling. So there's my 30 degrees. And then this is a chandelier. What does the chandelier look like? I don't know. Like a Christmas tree, evidently. Nope, I was trying to do something different than what I drew originally. I'm just going to go with the first thing that I ever thought to draw, which was kind of these concentric circles. Some kind of 80s looking chandelier. Okay. So there's our picture, and the object that we're going to draw is for it's this chandelier, right? This is our object. So we can identify the forces acting here. There's definitely weight, right? So I could say that here. There's weight acting here. There's no drag. There's no normal force here because it's not touching any surface, right? There's no force directly from the ceiling here. There's no friction, static or otherwise. There is tension, though, right? And there are two of them. We'll say times 2, right? Because there are two chains here. So let's draw some axes. I'm thinking straight up and down is going to make sense. I could tilt it 30 degrees one way or 30 degrees the other way, but I'm thinking straight up and down makes sense. So let's draw that. Hey, where did it go? Didn't mean for that to happen. Okay. Alright, and this is the x-axis, and this is the y-axis. So there are these three forces that we're going to draw. I could draw weight first, and weight is straight down right here. I have a tendency to draw these a little off axis, even though it is on axis, mostly so you can see it. So I'll make it just a little longer, why not? Okay, there's weight. I'm going to label it. I think that's going to be useful. So let's call it weight. We could call it F sub g as in force due to gravity. I try not to call it g because g is already taken by the acceleration due to gravity. But really, the variable name you choose isn't all that important. It just needs to be meaningful to you and maybe to someone else who reads the problem if they ever are going to look at your work. Okay, so that leaves these two ropes pointing up and to the right and up and to the left. And I'd like to see, like, what angle do they make with the x-axis? Well, the x-axis is right here on the picture. And you see that it's parallel to the ceiling? And then there's this this line that cuts through it. If you remember geometry, let's use, I don't know, some other color, turquoise. This is an alternate interior angle, so it's also 30 degrees. You can argue that using other geometry methods as well, but alternate interior angle is good enough for us. So it's going to make 30 degrees with the x-axis. That's what I'm saying. So, you know, the ruler actually tells me angle. So there's 30 degrees. Look at that. There. So let's put it right there. And I want it to go, I don't know, up to about here is good enough. That's pretty good. How long is that? Because the other one's the same length. It's like almost 2.5 tick marks. So then I want 30 degrees the other way. I would never be this careful if I was drawing it with a pen. There. Come on, you can do it. Okay, that looks great. So let's draw the end of those. These are both tension, but they're different objects, so I'm going to call it T1 and T2. Those are vectors. Great. Again, I could call this F sub t, but if I call this F sub t, I have to call it F sub t sub 1, and the other one's F sub t sub 2. And I don't like lots of subscripts, so if it's going to cause me, if using F sub something is going to cause me to have to use multiple subscripts, I'll just drop the F. Okay, that's our free body diagram. That's it. I want to mention one thing I was careful about. You can see that T1 is going to break into T1x and T1y. Do you see that? This is why we learned how to decompose vectors. T1y and T2y should both add up to exactly offset weight, right? Because they're each sharing half the load based on symmetry here. So I was trying to be careful to draw T1 and T2 so that their vertical components would add to the weight. Also, see that we had to use a second subscript. So if I had used F, I'd have to say F sub 1 sub, no, F sub t sub 1 sub x, which is just getting to be ludicrous. Okay, let's do one more example. Cool. And of course, this example involves a monkey. So a monkey relaxes on a tree branch. The branch makes a 15-degree angle with the jungle floor. Draw a free body diagram for the monkey. Okay, so the first step of every physics problem is to draw a picture. So I need to draw a tree branch. Let's start with the jungle floor. And then the tree branch goes off at 15 degrees. So there's 15-ish Okay. And how do you draw a monkey? I don't know, let's start with the body, and then like a head, and some monkey ears, and some legs. And he's just like relaxing, right? So he's got his legs crossed and his hands behind his. Great, that's awesome. Let's make a list then of the forces. So he's in a jungle, and the jungle is on Earth, and Earth has gravity, so weight. What else is happening? Well, he's sitting on a tree branch at an angle, so he's not sliding down, so there must be friction. And he's not going through the branch, so there must be a normal force. Past that, I think we might be good. I think that's it. We could be careful, actually. We could say, what kind of friction is it? Well, he's not sliding, so that friction is static friction. And static and kinetic friction are similar. Static friction prevents sliding, prevents slipping, and kinetic friction acts against velocity to slow something down. Okay, so I think we're ready to draw this picture. So let's draw some axes. Our x-axis here is at 15 degrees to the horizontal. And then the other axis here is going to be 75, it looks like. Yeah, this is great. Okay. So we'll call that positive x direction, the positive y direction. And what do we have? We have weight. Let's start with weight. Now weight points straight down, right? And we're kind of choosing how long we want this to be. So that's pretty good. We could label it, right? And then normal force points perpendicular to the surface always. So the normal force is going to point straight in the y direction. So I want to take a second and think, how long is that normal force? Again, it's not super critical that we get this exactly right now, but it helps to have it kind of to scale. So the normal force is going to exactly match the y component of weight, and the y component of weight dots over to about there. So it needs to be about that long, which is 1, 2, 3, 3.5-ish tick marks. Maybe those are centimeters, I don't know. So that didn't work. Let's try it again. So 3.5 is about to there. So again, you can kind of see it's hard to see that, but when I add more ink, it just makes it look terrible. Which is why I often draw these off axis. So in case you were wondering when you see that. Okay, so there's my normal force. Let's label it. Sometimes I'll go F sub n or just n. Okay. The only other force then is friction, and friction is preventing sliding. Now, in this case, it's pretty obviously up the ramp, but that's not always the case. Friction can act down the ramp if there's some other force. Like, let's say I'm trying to slide a box up the ramp. Friction could actually point down the ramp. And static friction is even harder, because static friction is whatever it needs to be to prevent sliding. So you could have a case where it's pointing up the ramp, you could have a case where it's pointing down the ramp, and we'll see an example like that in another video. So for now, let's just draw the static friction. It does point up the ramp in this case, up the branch, and it's going to be this length of the x component of weight. So it's just a little arrow pointing like here. There, that's friction. Sometimes if it's static, we'll say F sub S. Okay, that's pretty good. Or you could say F sub F, but again, this is static friction, so it could be F sub S, which is confusing. The only other thing I might do is label this to angle. And again, because this is such a narrow angle, it's pretty clear that that's the 15 degree. Okay, so we will see how this makes it lots easier to fill out Newton's second law in a future lecture. So thanks for watching.